So today we're going to talk about electric force and electric charge. So we're going to talk a little bit about those two things and how they come together with the Coulomb's law, and then we'll spend some time working with all these things. So the smallest amount of electric charge is the charge of the proton and the electron, and here is what they are in SI units, the magnitude, and of course the proton is positive, electron is negative. Now what we'll do from time to time is we'll look at student comments that have commented on certain things like this. And so here's a question a student had. If nothing makes a charge negative or positive, since we only use these terms to describe why a charge behaves a certain way, what is stopping us from calling electrons protons or vice versa? So again, this is a student question, really good question. Basically, there's nothing stopping us. This is historical. Historical before they really knew how this stuff worked. Okay, they define a certain type of charge as positive and a certain type of charge as negative. We'll talk much more about this as we go on, but again, there is really no good reason. The electric force works this way here. Right, so like charges repel and opposite charges attract. So there are a lot of problems where this is essentially the key piece that you've got to remember, is how to draw these forces here. Okay, we're going to do some examples, but that's really what it is. And so when there's positive and negative, the forces are equal and opposite and they attract. When they're the same charge, these two negatives here, the force is repelling. And the force will be directed along a line that separates the two charges. So if you draw this line in between here, the line's going to be the force will be parallel to that line. And then the other key piece we're going to use is what's called superposition. And so what do we do if there's more than one charge that can apply a force to our point charge? So here, we get a pretty good feel for what happens if there's just two, but if there's more than one, we have to use superposition. And it actually works out about as simple as can be expected. The law of superposition says all we have to do is add all the forces acting together. So this brings us back to 2A when we did a lot of adding of vectors. Again, some student comments. An example at the end of the pre-class video, right? So often with these lectures, there'll be a pre-class video, so you can go back and read that, and it's sort of a more fundamental look at some of this stuff, where during lecture time it's a little bit more practice, so you can go back and look at that. And so when considering the force caused by B or C, is it always okay to consider them as forces acting separately on A? And that's exactly right. That's what the law of superposition says. Okay, that if there's more than one charge, we can look at them individually and then add up the result force that we might get later. And another question regarding the superposition principle, how do we actually know that multiple forces in charge distribution simply add vectorially in nature? If so, what are some specific evidences of this? This is actually a really great question, and unfortunately my answer is just that's the way that it works, right? We've never seen it not work. You can kind of imagine that, if you just think about it simply, that you can kind of argue in your head that, well, that kind of makes sense. But unfortunately, we can't really say much more than that. So great question there. So let's do an example of this. So we're going to stop periodically and do these clicker questions. I really suggest that you stop and think about this first before you get my explanation. Even better if you can get some buddies to watch this with you. That can be super effective. All right, so let's go ahead and think about this one, and we'll talk about it in a second. All right, so this is a classic example of using this principle of superposition. And this is also a classic example of something you can have as a test question. So we're going to treat these two or these particles separate. So the idea here is there's these three charged spheres arranged as below. They all have the same charge magnitude but different signs. And we want to know is what's going to be the force on charge A. And of course, it would have been nice if we had written charge A ahead of time there. So actually, why don't you stop there and think about this again with that being charge A. All right, so what do we do here? Well, we look at the force from these other charges. So from this one right here, right, the force is going to be something kind of like that. All right, this is two negative charges, and so let's call this B and let's call this C. And so the force acting on A from B will be pushing that way. It's a repulsive force. And then the force on A from C is going to be something kind of like this over here. All right, force A on C. And so this is one of these situations where first of all, hopefully you can argue in your head that basically the angle for both of these should be the same. And so if I break these two forces into components, and that's what we're going to end up doing a lot of times, is breaking these two forces into components, I can argue that this angle and this angle here have to be the same. All right, and so if that's in fact true, then what happens is the up and down parts are going to cancel out, and the moving right part is going to double up. And so you can say that in this case here, the answer should be pointing that way right there. And again, this is using our knowledge of forces repelling and attracting, and then our knowledge of this idea of principle of superposition. So let's move now to maybe a little bit more of a tricky problem. And so here's the kind of problem you'll get. In the figure below, two fixed point charges are arranged. So you get two charges, one positive, one negative. We tell you their charge. This little thing here means microcoulombs, which you can look up as 10 to the negative 6 coulombs. We're on the x-axis, so we'll assume this thing is the x-axis. Could you put a third charge so it would experience no net force? And so that's the question, and so let's go through and deal with that. But first, let's look at some student questions about this. So I'm confused, student says, by exactly what a test charge is. Is it the charge creating the electric field? And so again, this idea of a test charge is typically in these problems you'll have some set of charges. Here we've got our two charges, this positive and this negative. All right, and the test charge would be the one that we're sort of, acting with. So in this case here, the test charge would be the one that we're going to try to put on the axis and not feel a force. Generally, this test charge is considered to be a really tiny charge, so it doesn't really affect anything else going on, right, is one sort of thing. And so it's also, student asked, since opposites attract and same repulses, the particles shown are not stationary. So that's another good point, is in general with these kind of problems, unless it's stated otherwise, you can assume that they're like stuck in there somehow, like there's glue sticking them to those 2 points there. So this positive and this negative are sort of stuck there. They're not going to move. And so we're trying to find, where is the point that I can put some charge on this line where there'll be no force caused by these two charges, Q1 and Q2. And so if there are forces between the particles, would they move? Kind of the same question. So totally, if these things weren't sort of stuck in there, they would be applying, they would make each other move. But we're going to assume that these two charges, Q1 and Q2, are going to be stuck there. So in a problem like this, you can always assume that unless it says otherwise. And sometimes it'll actually say that they're stuck in there. It just sort of depends. All right, and so I think one way to kind of unpack this is to start with a question like this here. So again, here is our axis. So in the figure below, two fixed point charges are arranged. Now, first of all, just where on the x-axis could you put a third charge so it would experience no net force? So the first part of this is to sort of figure out in your head where this could be, and this is where you're going to have to reason. Okay, and so the choices are to the left of Q1, in between the two charges, to the right of Q2, or then it depends on whether the third charge is positive or negative. Okay, so just like last time, stop here, think about this, possibly talk with a friend if you can, and I'll tell you more about it in a second. Okay, so hopefully you had a time to think about this, and you got A as to the left of Q1. So let's look at this and try to unpack this a little bit. And so here's what a student said when asked this question. So a student said, in between doesn't work because regardless of positive or negative, you get a net force in one direction. To the right of Q2 doesn't work because the magnitude resulting from Q2 would always be greater than Q1 due to the higher charge. And to the left has a possible answer since Q2 has a higher charge magnitude and larger distance. And they counter each other because of our equation, Coulomb's law. So again, we're going to use this equation, Coulomb's law, and you can look back in the pre-class video to sort of follow up on this. But the way that this works here is the force depends on two things. It depends on the charges and the distance between them. And so let's sort of look at how this would work a little bit. So I'm going to draw like a little sort of couple regions here. And I'm going to look at, okay, so suppose that we put, so we're going to put our charge right here. Okay, we're going to put our charge right here and our charge right over here. So this is sort of the three cases, right? So the charge right there, number 2, charge right there, and number 3, charge right there. Now this is the region here where we're dealing with a positive charge, and this is the region here where we're dealing with a negative charge. So if this charge was positive, okay, then the forces would look like this. So again, imagine that it's over here. So the positive charge, and we'll call this is Q1 and Q2. So here I'll have is force 1 is pushing this way, and force 2 is pushing this way. In the middle here, if it's a positive charge, okay, from force 1 is going to be repelling. Again, we're just using this idea of the that like charges repel, unlike attract. and then this idea of superposition with the forces, just like we did last time. So this positive, if this, then it would feel a force this way from F2, and then the positive charge, if it's in this region over here, is going to feel a repulsion from F1 and an attraction to F2. All right, so this is with the three cases here. And it's like that person said in the middle here, right? There's no way that you can put the charge here so that it'll cancel, because those two forces are going to be pushing to the right. Okay, and so you're not going to have any impact there. You can't cancel that out. You could possibly cancel out on the two sides, but what the person said, which was really key, was that over here, okay, on this region, in this region 3, you're always a little bit closer to the 4 charge, the bigger charge. And so there's no way this one can be strong enough for these two forces to actually cancel out, right? So again, according to Coulomb's law, the magnitude of our force is K Q1 Q2 over R squared. And so it depends on how strong the charge is, but also the distance of separation. So over here, because I'm always closer to the -4, it'll never cancel out. Over here, okay, you'll get to some point, maybe it's like right here, just for kicks or whatever, right? This point right here or something, where you're going to be close enough to that positive, where the force from that positive, which is a 1 magnitude, okay, is going to be equal to the force from the 4, which is going to be bigger. And so this would be possible that this would work out. Now, if we do the same thing for the negative, all right, you'll find that it works out all the same, because everything's kind of switched. So if it's a negative charge, then the force, again, we're putting the charge here where this 1 would be. If it's a negative charge, then what would happen is F1 would push this way and F2 would push this way. So it just switches, right? It'd be attracted to force 1 and it would be repelled from charge 2. In the middle here, again, you'd have them pointing in the same direction like this here. And then finally over here, you'll end up having them move in different directions like so again. It's the same sort of rationale. So it's possible they could cancel out in region 1 or 3, but because you're always going to be closer to that -4, this is the correct region. And the way I kind of think about it is I think about these charges as people talking. Okay, and so this is the bigger charge. This is like a person yelling. This is the smaller charge. This is a person whispering. Okay, if I'm over here in region 3, I'm never ever going to be able to hear the whisperer over the yeller, because I'm going to be closer to the yeller no matter what. Whereas if I'm over here, right, there's some point where I get close enough to the whisperer where I can actually hear them as much as the person who's yelling. So it's the same sort of idea as that. All right, so now that we've looked at a few of these more conceptually, let's try to look at one a little more that we have to use numbers or to be a little bit more quantitative with. And so again, this is our Coulomb's law. This is again is the electric force due to a point charge, which we'll focus on for this, a lot of this first lecture here. So first of all, this is a vector. We sort of talked about this, but that's something that maybe you haven't used in a while, so we just want to get more used to that. Now, everyone does this a little bit differently, but when I'm doing these problems here, all right, I just think about the force as being the magnitude, all right, and then I'm going to use my head to figure out which way those vectors are pointing. I think that's easier. Everyone's different though, and so if that happens, then what that means is you're just going to plug in the magnitude for the Q1 and the Q2. You're not going to worry about whether it's positive or negative. So you can do it that way a little bit more quantitatively, but I think for me it's just easier to just always, when you're dealing with forces, to use positives for those Q's and then use your brain to figure out which way it's pointing. And so someone asks here, well, when do we include the negative sign for the charges? So again, in my opinion, I don't. Okay, and it can be kind of tricky sometimes. And so we'll do a problem here that kind of maybe shows some of this here. So here's a kind of problem that you could get that wants a quantitative answer. And so you've got this setup here of charges. Again, these charges are assumed like they're sort of tacked into the wall. They're stuck there, so they're not going to be moving. And we want to find what the force would be at that particular moment. And so in this picture, you're given letters instead of numbers, which is always kind of a pain, but it's good to sort of practice with that. And the idea is that you're trying to find the force on the Q charged sphere. And so the three charges are Q, 5Q, and 3Q. So first of all, in this picture here, Q isn't told to you. So it could be like, you know, -4 microcoulombs or something. Who knows, right? So it could be negative, it could be positive. But what we're just going to do is assume that it's like, you know, positive. We're doing our calculations here. And the thing is, you could sort of plug in that number when you're all over. And essentially, if it's, you know, it would sort of change the sign potentially. So let's go about solving this then. And so the way that we would do this is, again, we would look at each of the forces individually and then add them up later. So since these are, whatever they are, they're the same charge, then we know that the two forces will be repulsive. So first of all, just take a second and make sure you can convince yourself that this is in fact what the direction of the charge F3Q would have on this Q. It's going to be pointing straight up. And then from this 5Q, it's going to be pointing that way over there. So this would be the directions that we're going to use. So first of all, convince yourself that that's true. And then the next part is to get the actual magnitude, we pull out that Coulomb's law. And so I'm going to use this little constant K. And so what we do here is we put in the two charges. So I'm going to start by doing the easier one, the force from 3Q. So that's what this means here. This is the force from 3Q on our Q. And so my Q1 would be this 3Q, and then my Q2 would be just the Q. So again, when we're doing this equation, you know, there's two charges you're dealing with that determine the force F3Q, and I want to put them both in there. And then that over R squared part is the distance. And so here it's just this distance d squared that we're told. All right, and so if I clean that up a little bit, I'll get, let's see, 3, I'll go through and erase this here. So if I just clean that up, I'll get 3k q squared over d squared. Now technically, this is a vector, and so what I'm going to want to do eventually is write it out in its component form, and everyone does this a little bit differently. And so I'm just going to, you know, use our sort of typical, this would be our y-axis, this would be the x-axis. And so in this case here, it would be 0 in the x-axis, and it would be 3k q squared over d squared in the y direction. That would be our force, this blue arrow that I drew over here. So my only question is, how do I know what direction the force is if I don't know if the charges are positive or negative? Well, again, in this case here, I don't know if they're positive or negative, but I knew they were the same, so I knew they had to be repulsive. In this particular case here. So now what I want you to do is do the harder one. Okay, so I want you to figure out the force of 5Q on Q. And in fact, so I want to say, what is the closest down there to the magnitude of the x component of the force on the 5Q charged sphere on the Q charged sphere? So again, this is something that I really think you should stop and work through before you see my explanation. All right, so hopefully you got this answer here, answer C. And so let's just go through this and sort of show how this works. So again, the way I would start this is I'd say, well, like I did last time, let's find the magnitude of the force of the 5Q charge. And so that's going to be this K. And then just like last time, right, I put my two charges. So the 5Q and then the Q, those are my two charges. And now this is a little bit trickier to find this distance squared. So I'm going to call it R. Right there, and that distance is going to be the distance between the 5Q and the Q, and so it's going to be the hypotenuse here in this particular picture here, right? And so what's that hypotenuse going to be? Well, if you think about it, that R squared will end up being d squared plus d squared. All right, and so altogether that'll end up being 2d squared. And so if I plug that in from over here, then I get the magnitude of my 5FQ is going to be altogether again, just 2 squared down there, so it'll be 5 halves KQ squared over D squared. Okay, and so again, that's assuming, this is just the sort of arrow pointing down to here. And so now, so that would be the magnitude of the 5Q. We were asking for the X component. And so what you got to do then is to draw yourself a little picture. And so here, this would be my force of the 5Q. And I know that it's going to have an x component and a y component, and I want this x component. All right, and so the key is figuring out what this angle is here. Well, so this little picture here is going to be determined by this particular arrow that we have here, right? And so if we actually can maybe just draw this on here, it might be a little bit better to do that. And so, like, you know, we're talking about this triangle that looks something kind of like this right here. All right, and so this angle is 45 degrees, and so by that same token, this angle will be 45 degrees as well. Okay, and so this is where, you know, I think this stuff can get tricky, because this is, you know, doing vectors, which again, some of us haven't done in a while. And so that angle would be 45, and so this component here, this x component, would be the magnitude of magnitude of force of 5q times cosine of 45. And then of course this one over here, just to be consistent, would be this times sine 45. Now since it's 45, it doesn't really matter, but it's still nice to write that out. And so my force of 5q, the question was asking for this in the x component, would then be equal to this, and so it would be 5/2 kq squared over d squared, and again this would be times cosine 45, and when I went through and multiplied that, I got something pretty close to 1.76 kq squared over d squared. Now to finish this problem, we're almost there, and so if you remember last time, I wrote out the force from the 3q charge, and that was a 0 here, and then something like 3k q squared over d squared. And we just figured out the force from the 5q. And so because it's a 45-degree angle, what's nice is it works out to be the same force in both directions. So this would be k q squared over d squared times the 1.76, and then 1.76 times k q squared over d squared. And one thing to be real careful of is my signage. If you remember, this is the x and the y axis. And so these two vectors here, the force of the 3q and the force of the 5q, in this particular problem, they both work out to be pointing in the positive directions, right? So positive y, positive x. And so all of these things here are going to turn out to be positive. So that works out pretty nice in this example. And so to find the total, you just add these together. So the total would be something like 1.76 k q squared over d squared. And then here, 1.76 plus 3 gives me 4.76 k q squared over d squared. And so this is my total vector, right? So in some ways, this is the final answer, right? And so you know, you sort of done all the physics, you've done the math. Now, unfortunately, in this problem, and this is something that the book loves to do, is they want the total force in terms of magnitude and direction. So we got to go through and figure that out. But you've sort of done, I would say, all the work at this point, which is nice. So let's maybe stop for a second and see if you can work through the magnitude and direction, and then we'll talk about it in a second. Okay, so here's how I set it up. And again, everyone does this a little bit different, so it's kind of up to you. But we know that my F total has these two components here, 1.76 times k q squared over d squared, 4.76 times k q squared over d squared. Now these k squared over d squared parts are just kind of a pain. You can sort of think about them as being the units of it if you wanted to. And so in a sense, you have this vector where the x is 1.76 and the y is 4.76. And that's what I drew right here. So 1.76 and 4.76. To define the magnitude, you get 5.07. So again, technically, in this particular problem here, that would be 5.07 k q squared over d squared. So again, like I said before, in theory, they could give you a q and a d, then you could plug it in now and get it what it actually was. But in terms of letters, this is the answer. And so at 5.07. And then to find the angle, right, I just sort of decided to find this angle here. So this problem was kind of ambiguous. It doesn't actually ask which angle to find. So if someone asked about that, you know, when you were defining direction of force, what angle do you use? Well, in this case, it's kind of up to you, but in general, oftentimes they'll let you know. But what did I do here? Well, I used inverse tangent. So I said inverse tangent of 4.76 over 1.76 gives me 69.7. And so that's my magnitude and direction for that one there. And so this is the kind of example problem that you can end up doing. Again, that's more quantitative, but really fundamentally, it depended on all that stuff we were talking about, the laws of superposition, and then whether the forces are attracting or repelling. And so there's lots of ways you've got to be really strict with your physics and make sure you're following along correctly. All right, and so let's just stop and look at, these are some student questions that I've gotten about these type of topics. So are there any faster ways of calculating the net force than adding up all components when there are a large number of forces? And so basically, no, right? We'll see soon that in some cases where there's extreme symmetry, there's ways you can use calculus to help you. But if there's not some really nice symmetry, then really there aren't really, so I just went through an example of finding the force on one charge from two other charges, and it took us a while. If I was to be a real jerk and have you find the force from three charges, that makes it even worse, and then so on and so forth. So basically, it's the same principle, it just gets harder and harder as you get to more and more charges. Is there an equal and opposite reaction of force of attraction of oppositely charged particles? Why aren't they always in equilibrium? So this is someone that's a little bit mixed up with Newton's third law. So I think what they're talking about is, imagine there's like a negative charge and a positive charge, and of course we talked about it that the force on those charges would be equal and opposite pulling inward, right? And so that's totally true that those two forces have to be the same. But when you're talking about equilibrium, what you'd be looking at, you'd say, okay, well, let's look at this positive charge. What are the forces acting on that? Let's just assume that these two charges are like in deep space. So the only thing there is just this negative charge. And so if that's the case, then this force is going to be pulling on it, and it's going to accelerate that charge. All right. So just be careful about that. And then, can you find the force on a particle by two other particles without knowing the third particle's charge? You cannot, okay? And so, there's like the example we looked at on that x-axis where we knew where to put the charge independent of its charge, where they would cancel out. And so that's kind of a special, we knew that it would be 0 at that one point there. But in general, you need to know the third particle's charge. All right, and here's another example. So here's the kind of thing, we're going to see this a lot this semester. We're going to see example problems where what I call them is it's sort of like a combination of a 2B problem and a 2A problem. All right, so here there's a problem that's got a little bit of 2B, but it has a lot of 2A in it as well. And so you need to be real cautious of that. So let's go through and do this example here. This is an old test question. And so it says two small spheres with equal unknown mass, and so two small spheres with some sort of unknown mass, we don't know what their mass are suspended by lightweight strings of length 12 centimeters, as in this picture here. And when a charge of 3 nanocoulombs is placed on each sphere, each string makes an angle of 20 degrees with the vertical in equilibrium. And in this problem here, in this particular test problem, you were tasked with trying to find the mass of those particles. All right, and so so these two particles here, what is their mass? And so let's go through and start thinking about this problem here. And so here's the way I would start a problem like this. So this is really a Newton's law force style problem. Okay, so they got these two small spheres here. And so let's just look at the one ball. Let's look at just our left ball there. Excuse my French. And just think how many forces act on that ball. So stop here, think about it. Again, ideally ask your neighbor if you're working with somebody else, but how many forces are acting on that left sphere? All right, so if I was to draw that left sphere, it would look like this here. And so what are the forces? Well, there's our good old friend gravity, mg. There's what I would call the tension of the string pulling up right there. And then there's over here, this is our new 2B thing, the force from the electric charge. And so then all together, there would be 3 forces acting on the left sphere. Right, so again, with these kind of problems, the first thing you want to do is always start out with your free body. With these kind of problems, you always start with your free body diagram. It's a good one to do. So now another one, just to kind of work ourselves through this. So okay, so we did that. So now what is the correct expression for the force pulling up on the left sphere? okay, in terms of the tension and then that angle of 20 or some sort of angle in the problem. So go ahead and think about this. So what is the correct expression for the force pulling up on the left ball, left sphere, and think about that, okay? All right, and so here's how I would do this. And so here's our sphere, and the tension is this way. And so again, we're going to do these kind of deals where I break that force into its two components, what I'll call the x and the y. So this is the tx, and this is the ty. So the real trick to this part is realizing where that angle of 20 is. And from the picture, hopefully you can see that this angle here is that 20 degrees. And so the force pulling up would be by definition our ty. And so ty would end up in this case being t cosine of 20, which is answer B. So hopefully that's what you got. And so now let's head home and try to use all this and put this all together to solve for the mass. So I would ask that pause this and see if you can go through and solve for that mass right now, but before I go through and do it. Okay, so the first thing is let's finish our free body diagram. So I always like to so again, this is our left sphere, and so the force up on that we just determined was t cosine theta, which means the force pulling to the right will be t sine of theta, so sine of 20. And then the force of the electric force, as we described, would be pointing this way over here, and our good old friend mg will be pointing down. And so then we can look at, I like to do this, think about, okay, so look at the x and the y. So this is an equilibrium, and so in the x direction, we get an equation that says t sine 20 is equal to the force of the electric, the new one. And in the y direction, we've got t cosine of 20 is equal to mg. And so at this point, the physics is done, and this is just going to be some math and some geometry. And so we got these two equations here. One really slick way to do it is to actually take these equations and divide them by each other. Okay, so you can kind of do that. But you can also, just to go a little bit slower, you say, okay, well, take my y equation. So I can say that t is equal to mg divided by cosine 20, and then plug it into t over here. And get rid of t because you don't care about that. And so you'll get mg sine of 20, or cosine of 20, and then that's going to equal, again, the force of the electric. Now we can take that, and we're trying here to solve for m. And so I can go through and solve for m. So first of all, these two guys together, sine over cosine is tangent. Okay, so I can sort of rewrite that left side as mg times tangent of 20, or theta, whatever you want to call it. And so then here, I can solve for that m and just say that it's equal to the force of the electric force divided by g tangent of 20. And then the last step would be, this is sort of the 2b part of the material, is plugging in our equation for Coulomb's law for that force of the electric. So it's q squared over r squared. So that's plugging in for this Fe, and then times g tangent of 20. And so let's look at this. Tangent of 20 we know, g we know, k is that constant we described in our coulombs, and q is actually given to us over here as 3 nanocoulombs. So the one thing we don't know is that r squared, and so that's a little bit tricky. Let's go through that a little slowly here. And so in our picture here, so stop for a second and just try to draw what actually is the r that we're talking about in this case. So give that a try, and I'll show you in a second. And so, okay, so hopefully you got this. This is what I call the R right here. Okay, and what we can do is we can actually find 1/2 of it, okay, sort of like this length right here, by looking at this triangle. Okay, so that triangle there, so this is sort of R divided by 2, this side over here, this is our 20 degrees, and we know that this is 12 centimeters, which I'm going to write as 0.12 meters. Okay, so basically that side over there, r divided by 2, I can say that r divided by 2 is going to equal what? Well, it's going to equal this side of our particular picture there, and so I'd call that 0.012 times sine of 20. And when I figure that out there, and I solve for my r, I got that r came out to be so when I did this here, so I got that this r divided by 2, so it's 0.012 times sine 20. And so when I pull up my calculator here, I get 0.041, 0.041, and then when I multiply that by 2, I get 0.082. So again, that's going to be put in over here. Everything else we know in this particular problem. And so when I did this, I got a mass of 3.37 times 10 to the negative 6 kilograms. So again, that's the style of problem that's going to come up, sometimes in 2B, where, again, I would say it's kind of a 2A problem plus a 2B problem. Again, there is going to be, I do have these pre-lecture videos for most of these lectures, so you can always go back there for kind of a refresher, read the book, and if you have questions, please post the questions for our active time that we're going to have later in the week. Thank you.